Right, so today we're going to take on the network topology. Last time we had the network types and now network topology. The course is called network cabling, so might as well talk about networks and things, eh? All right, so here is network topology. Right? These are the symbols for different topologies for the network. So here's a ring, mesh, star, fully connected, tree, inline chain, or bus. We're going to tackle the 1, 2, 3, 4 of those. We're going to talk about the ring, star, ring go star, ring, star, inline chain, or bus. All right, so let's kick off with the definitions here. So B does not show up this week. No, this week is just the A groups, subsections. And the next week, we're going to do the same lab, but for the B section. So the A can have some extra time to watch those videos that are so hard to watch. All right. Cool. All right, so let's talk about some definitions. What do we mean by topology? Topology is the arrangement of a network, including its nodes and connecting lines. Nodes, what's a node? A node is a device, it's a smart device. A node is a device that is connected into a network and works within the network. So it could be a laptop, a PC computer, it could be a wireless device such as cell phone or a wirelessly connected laptop as well. So it could be access point, it could be a security camera, it could be any kind of a peripheral for security system, security alarm, fire alarm, North code system, PA system, anything that is considered a smart device. What's a smart device? A smart device is a device that has some sort of artificial intelligence, if you can say that, that is connected within the network and it's actually communicating within the network. All right. So again, the net topology is the arrangement of a network, including its nodes and connecting lines. Connecting lines. What do we have? We have copper, which we're going to be mostly talking about during this whole course. We also have optical fiber, which we'll also cover that in some detail. And we have wireless, which we're not going to cover in this course, but we're going to talk about some possibilities. Actually, when we talk about the media converters, that also the media converters cover the either copper to fiber or copper to wireless. So now, when it comes to network geometry, we'll talk about that as well within the topology. It is the physical, we consider the physical topology and the logical or signal topology. Physical topology is how those networks, whatever the devices are, how they are hardwired. And the logical or signal topology is independently of how they are wired. It is the signal, how the signal travels within, and by the end of this class, you'll know what I mean here. All right. Now, when it comes to basic elements of network presentation, on the left side we have hosts or nodes, which would be devices. So we have computers, wireless access points, routers, switches, hubs, bridges, gateways, and modems and whatnot. Printers and other devices such as IP cameras, right? Security cameras. Usually it'll be a security camera. Right? And of course we have connecting links. So what do we have? Copper, fiber, air, which will be the wireless. Right? Now, let's start with something that's called a ring topology. Here is some kind of visual symbol for a ring topology. It looks like a ring, not very ringy, but it still is a ring, right? So in ring, each node or host connects to two adjacent nodes in a continuous pathway for signals through each node. Right? So here is, so this is a device and it's connecting to any other device through a device. So every device has two adjacent ones, right? So it's a ring. Data travels from node to node, with each node along the way handling every data packet. So basically the signal is handling by every node. So if this device wants to communicate with this device, the signal has to go through this device, right? Or if you want to go other way, it will go through all the other devices and get to this device here. We'll talk about that as well. Every node acts as a repeater. So basically, if there's a message to this node from that one, and if the signal goes this way, this device is going to get the message. It's going to say, no, it's not for me. I'm going to pass it along. This one, oh, no, it's not for me. I'm going to pass it along. This one's going, oh, yeah, this is for me. Okay, I received the message. All right. So, not a big philosophy when it comes to that kind of a concept here. All right. Ring topology hardware. Now, this is the big hardware. Now, when we're talking about the laptops, of course, the cards are going to be much smaller, but these are kind of easier to show. As the technology advances, there are different models of the network cards, and most of them right now are pretty much built into the motherboard of the devices, or sometimes they're interchangeable depending on what the device is. So a single port NIC or two-port, double-port NIC, network interface card, right, NIC, which NIC could be used for a ring network, a single port or a double port, right? NIC is the network interface port. Well, if you go back, if every device, yeah, there we go, double. If every device is connecting to two adjacent ones, so you don't need double port. Now, double port, if you are considering the physical topology, when it comes to hardwiring this, can we use single port for ring topology? Technically, yes, but we're not going to go into that detail just yet. But I'm going to, at the end, I'm going to show you what it means, what I just mean. But when it comes to hardwiring or the physical topology, yes, absolutely, we need the double one because of the nature of this network here. Right? All right, ring configuration. This is the way signal travels, with every node again acting as a repeater. Right? So it's just another visual for this type of topology as a ring topology. Right? Now, difference between a ring and a token ring. Here's a group of buildings that are connected as a single network. All right. Some of them are, some of the buildings are connected to fiber. Some of them are connected possibly to a copper wire, and some of them are connected wirelessly. Right? So those buildings are connected within a ring topology. Now, ring versus token ring, and here application, when or man. Okay, wide area network or metropolitan area network for just this type of network. But then again, ring the ring topology can be applied in the LAN configuration as well. Now, in the ring topology, the data only travels one way. So this would be a ring configuration. The data only travels one way. So there's a bit of a problem that could be happening here. If this computer wants to communicate with this computer, but this link is broken here, something happens to this machine, it's turned off or just basically breaks down, then the whole network is pretty much dysfunctional, because if the data travels only one way, through the ring configuration, it only can go this way, which means this machine will never get the information from the message from this computer here, right? Also, so basically, the token ring idea was introduced. Right? The token ring is a bidirectional ring. So if this device wants to communicate with this device, and it's going to start travel, it's going to call up the data to travel this way, and something happens to the network in here, and it's going to basically not find the node. So it's going to say, oh, maybe I should try the other way. So it's going to go try to do the other way, communicating the other way. So that's basically the difference between a ring and a token ring, is that in a token ring, the data can travel either way, in order to solve the problem of the network being broken in one way, in one spot. Right? Applications, LAN. So this will be the application for WAN or MAN, and this is the application for LAN. What happens is, do I have a picture here? Just going to speed up a little bit. Go here. This is a typical LAN configuration. What do we have? We have, oops, something happened here. All right. We have connecting links. In this case, this would probably be, in our case, Cat5e or Cat6, most likely Cat5e still. And this would be considered horizontal data run. We will talk about that as well in this class. Those wall plates where the jacks are connected through the copper wiring to something that's called a patch panel. A patch panel is basically a bunch of jacks arranged in a physical frame so the space can be conserved, right? To save the space. So all those wires home run to the home location where the patch panel is, and from there they're being patched onto the smart devices. Okay. So that's basically the concept here. Now, where are we? Where were we? All right. So now, let's say the switch is capable of only so many ports. There could be an 8-port switch. There could be a 12-port switch. There could be a 24-port switch, or it could be a 48-port switch. But if the network is so large, so huge, that the one switch is not enough, then there's a possibility of connecting switches or cascading them or connecting them together. So when they are connected to each other, they can serve as one big switch, and that could go endlessly, so to speak, right? And in this case, those switches can be connected into by the in a ring configuration. So the data between the switches is basically being exchanged, and a switch is it's a smart device that directs the traffic within the network. And then the switches can be connected to a gateway, and the gateway can be connected to a modem or a router, and the whole network can be connected to an outside world, right? So here's a ring configuration. The switches with multiple ports that are connected to the individual nodes or hosts or devices. Those switches can be connected in a ring configuration, so they can serve as one huge switch. So here's a application for LAN when it comes to ring topology. All right. Now, when we talk about switches, here are, when you download this posted lecture notes, I need you to watch this 7-minute video. Yes, and I need you to watch this video here, but only a minute and a half, about a minute and 42 seconds, in order to visualize what is the difference between hub, switch, and a router. Because when if you get a job in this communications field, it is a good idea to know what the equipment is that you're going to be working with. Now, this is a hardware-based course, not a software, not an IT course. Well, it's a sort of IT, it's a hardware part of the IT infrastructure. It's called network cabling. But when you're going to be sent for service calls or installations, well, this terminology is going to be used. So, it's a good idea for you to know what a switch is, what a hub is, what a router is, what a modem is. So this video explains the difference between hub, switch, and a router. And here is a setup in a chain or ring topology within the when we're connecting the switches. And past the minute and 42 seconds, this guy goes on about how to configure a specific type of switch. We're not interested in that for the purpose of this course, but watch up to 1 minute and 42. So they're not long videos, all right? So just watch those. All right, start topology. let's talk about the star. So here will be the symbol of a star instead of a ring. So there's a ring, and here is a star. Here's one main node, and all the satellite nodes, or satellite, I shouldn't be using the word satellite because the remote or the node or hosts or devices within the network home run to the one common device. Usually it would be a switch or a hub. Mostly switch, but you will know why. Okay, so let's see, in the star topology, each node or host of a network is attached to one central node. Usually it would be a switch. The central node is usually a hub or a switch, with the emphasis on the switch. Watch that video, this one here, and you will know why. The central node can also be another proprietary device, or another sort of proprietary, a dedicated device, such as NVR, which stands for Network Video Recorder, in a video surveillance system. So when it comes to a video surveillance, or basically security cameras, so those security cameras are smart devices. They are not analog anymore, although you can still see some of the old systems that are not so smart. They are not they're not communicating. The devices such as cameras are not communicating to the Ethernet cable, which is the computer cable, and they are just basically having a power and transmitting one-way video signal to the central location, which would be the recorder. Right? But now I'm not sure if you can still buy some of that. Maybe you can still buy some of the equipment to retrofit some of the old installations. But if you're going to do new installation, you're going to get something that's called the IP cameras, Internet Protocol cameras. So that instead of that being a switch, just a traditional network switch, it could be the NVR, which stands for Network Video Recorder. Star topology is the most common physical wiring configuration considering the horizontal network wiring. Here's a mouthful again. Okay, let's break it apart. Star topology is the most common physical wiring configuration when installing or hardwiring networks. And what does mean horizontal network wiring? We'll talk about that in a couple more slides. Star topology concept diagram. Here's a switch, and basically they are the nodes, or in this case just computers, but it could be anything. It could be camera, it could be something else, or wireless access point. They are connected right to the switch. It could be a VoIP telephone set. All right? Now, star topology, LAN or local area network configuration. All cables, and I put it in home run to one common point to a patch panel. So what does that mean? Well, there's a jack in the wall, and the jack in the wall is terminated, connected to a wire. The wire runs up the wall, through the ceiling, or maybe through the floor. And wherever it has to go through, it ends up in one common location, one home run location, where the patch panel is. Right? So that's what it looks like from the back, those patch panels. And the connection between the jack in the patch panel and the jack that's in the wall is just a dry wire connection. That's it. It's a link. Now you can plug something into the one side of that link, and you can plug something into the other part of the link. Right? So that's the idea of the network wiring or network cabling. Right? So there are a bunch of patch panels terminated, and each of those wires, they run right to specific locations. It could be somewhere on the desktop, so it could be somewhere within the wall, it could be somewhere in the ceiling, depending on wherever the device is. Notice this is probably most likely what I can see. This will be Cat 6, and we will talk about the categories, Cat 5e, Cat 6, Cat 7, and so on. This looks like a Cat 6 wiring because I can see it's a little bit thicker than Cat 5e. But one thing that gives it away is that Velcro is being used to bundle them up, right? And we'll talk about that as well in further classes. Basically, long story short is, if you use zip ties on the network cabling, you are squishing the cable. And when you're squishing that cable just by a zip tie, you're deforming that cable enough to change its specifications, right? So it's not going to be up to par as far as the ability to transfer the signal in a certain way. So Velcro is being used. Not only Velcro is being used, it's recommended that the Velcro is being used soft side in, right? Now, when we flip it around, that actually that's also yeah, well, some of it is yeah, that's also the rear of that, all right? So that's basically what the network cabling looks like when it comes to running the cables. All right. Now that's the front of it. This would be the rear wiring. This would be the front of this thing here. So now we have the other side of the patch panel. Patch panels. It's just a dry connection. The cable is terminated here. The cable is terminated in a wall somewhere, or whatever the destination is. And over here, there will be a smart device such as switch. Now, short patch cables are being used to connect the patch panel into the switch, patch panel into the switch. Every port, one by one, is connected to a port in the switch. That's how that's how pretty much things are being solved. And it's all about the ability to run those cables neatly, organize them in a very, very meticulous way, so it is serviceable, so it doesn't fail. There's a question: how big of a network is this example? This here, from what I can see, well, just take a look at this thing. This would be 24 ports. So 24, 24, 24, 24, 24, 24, 24, 24, 24, 24, 8 more, 24. You can just multiply 24 by whatever the amount of rack spaces you can see here, and you can tell how big this network is, right? Networks like that are not installed within a couple days, right? Some of them are big. Some of the networks, one of the biggest ones I have worked on was a long time ago. It was a Windsor PUC when we had 600 desktop connections there. So you can just imagine. It takes a little bit of time to. Yeah, wire management is clean. Yes. All right. So wire management is extremely important. It's so important that by nature the people who work on the data installations, after a while, it just gets into you. The neatness gets to you. It becomes part of your DNA, to the point that the network installers are the cleanest wirers that there are. Some of the who's the messiest ones? Security alarms. I've installed both, and somehow my brain switches. When I install the network, I do become very neat and clean when it comes to wiring, and because of the nature of installation of small security panels, it's just the way those things are organized. No matter how much you try, it doesn't. It just by the nature of things, the wiring gets a little bit messy. But that's the nature of things. Right? I'm not going to tell you to get messy, right? When I install the security alarms, just by the nature of things, I do tend to be more clean and meticulous as opposed to the person who just installs the security alarms. It's just like have you ever seen a drywall installation done by a retired tool and die maker? It's funny because everything is right down square to the millimeter. Right? Just a side note here. Right? So that's the front of the patch panel here. Okay, now when we talk about horizontal runs, what do we mean by horizontal runs? Here's a building. Right? If you just had X-ray vision and you would see inside the buildings. Right? Sometimes you might not want to have that X-ray vision, but that's besides the point. So let's say here's one floor, here's one floor, here's a floor. Here's the main cross connect. So this would be the main, well, sometimes it's called communications room or main telecommunications room, and sometimes it's called the electrical room, or a LAN room. Right? So in this case, somebody call it a network or main cross connect. Right? So in the main cross connect, all these blue boxes, all these areas where the equipment is that are marked as a blue box, this would be a part of something that's called a backbone, just like your spine. And from there, other devices are being branched off, just like a tree stump and the branches. Horizontal wiring. Let's say the second floor. It has a communication closet, and notice that in this case, those communication closets in every floor are one on top of the other in a kind of like a vertical way. Usually in commercial buildings, that is what you're going to see. The communications closets are aligned vertically, just so you can run the wiring between floors. Because telecommunications, as far as network installations, has become very important. So, same as, you can't, excuse me, you can't have a building without plumbing. You can't have a building without electrical installation. Now, it's unimaginable to have a commercial building without, or residential as well, but especially commercial building without a network installation. Right? So those closets, the communication closets, usually are going to be arranged in a, here's the magic word, riser, as the air rises, right? So it's a riser, which means the closets are basically arranged in a vertical way. So here's the vertical way. Now look at this. From the vertical way, from this closet, the wires extend horizontally. Okay? So here's the mystery solved. What does it mean? It's horizontal wiring. Yeah, it's wiring that basically home runs to one particular frame or intermediate distribution frame or distribution frame. So there could be main distribution frame, and it could be marked as MDF. MDF stands for main distribution frame. And there could be IDFs here. And IDF stands for intermediate distribution frame or intermediate cross connect. Just as an exercise, next time, Home Depot is very popular for that. Next time you go to Home Depot, look around the walls and you're going to see sort of like a small refrigerator size boxes, black boxes, mounted on the walls. And those are going to have labels that are going to say IDF-A, IDF-B, IDF-C, and so on. These are the intermediate distribution frames all around the store. Intermediate distribution frames are all connected to the main distribution frame. Right? Simple enough, right? And from the intermediate distribution frame or cross connect, horizontal wiring extends to particular devices. Why do we have a lot of intermediate distribution frames in a department store huge as, let's say, Home Depot, right? And I'm not associated with the Home Depot in any sort of way. I'm just using it as an example. It is because the horizontal wiring, when it comes to copper, Cat5e, Cat6, Cat6a, Cat7, all right, Cat7a, the longest distance you can get out of that copper cabling, and we'll talk about that too when we talk about the specifications, is 300 feet. All right. So that's why they have those IDFs placed strategically around the building. So the longest cable that is coming from that IDF is no longer than 300 feet. It's just a limitation for copper cabling, right? And then the IDFs are being connected to the main distribution frame, the MDF, through a fiber optic cabling. So optical fiber and optical fiber or fiber optics, they can go much further than 300 feet without losing a signal. Right? So here is, so that's why, and this is pretty much the model of any sort of basic concept of any sort of LAN used these days, right? So horizontal wiring means that the devices are connected to one distribution frame, right? All right. And structured network cabling, most popular. So basically, all the networks that are being installed today, right? Today we have 2022, right? So if somebody is watching this thing 5,000 years from now, this is how it was done in 2022, all right? So this would be a star topology when it comes to hardwired network, hardwiring concept, right? Now, we're going to talk about bus topology as well. What's a bus? If you look at the symbol here, there is just like, it's like a one main river, and all the devices are tapped in to that main signal. Well, when we do, remember when we do the lab, the PA system, the distributed audio, we are tapping in to the main signal line. So the main signal line could be considered as a bus, signal bus. It can also serve within the network. Now, up to early 90s, networks were used to be installed that way. In a bus topology, there will be one main signal for the network, and it would be a coaxial cable, and there would be the taps here, or terminating resistor here at the end. So they had to be terminated with a resistor, but there will be taps. You would tap into the signal and give it to the computer. Tap into the signal and give it to the computer. Now look how the computers look like. They look like old computers, all right? So bus topology, was used in LAN setting until early 1990s. Presently, and let's see when I prepared this document, I have to change that every year. I keep forgetting. Presently, all LAN horizontal systems are wired in a star configuration. Now, just because this system was used some time ago, that is basically it's not being used as far as computer networks, the bus topology is still being used in certain configurations. Like, for example, that distributed audio. Yeah, there you go. Similar to configuration PA system, yes. And I'm going to use the learning today, make a PA system to my kitchen so I can ask for food. All right, yeah, go ahead. Yeah, you know, innovation. We are all about innovation. There we go. Now, here's an example of a bus topology used. One of them was the distributed audio that we did. Then here's another example for fire alarm system, for example. How does a fire alarm work? Fire alarm has a fire alarm panel, and that panel has something that's called a zones. What's a zone? A zone is a circuit that senses certain type of signal condition, and there could be small alarm systems that are maybe just 2 zones, but there could be huge alarm systems that maybe have multiple zones, maybe 20, 40 zones, 50 zones, all right, depending on who makes it and for what purpose. But let's consider a single zone. How does a fire alarm work? A fire alarm zone, just look, it has those devices. It could be a smoke detector or a heat detector, or a pull station or some sort of a trigger. Like a kitchen system. There will be a heat trigger, right? But usually, basically, there will be sophisticated devices that would be a smoke detector or a heat detector when it comes to automatic detection. So let's say those are smoke or heat detectors, either or, and those are normally open. So the zone doesn't even see them because they're open. They are electrically open. There's no connection. When they trigger, they close. So they have the zone has a continuous bus line going right to something that's called the end of line resistor. When the zone sees that particular resistance that is with the end of line resistor, that zone thinks that everything is okay. Bus kind of a configuration. What happens when the wire gets broken somewhere? Well, then the zone is not going to see that resistor at the end of line, and it's going to see an open circuit, and it's not going to go into alarm condition, it's going to go into a trouble condition, and it's going to produce some annoying beeps in the lobby or wherever the panel is. So somebody comes over and looks at it and he says, oh, here is the phone number to call for the service company, get them here to fix it because something is wrong. It's not a fire, but it's a trouble with the alarm system. All right, but if any of those devices reacts, smoke detector senses smoke, is going to close the switch, it's going to short things out. So the zone is going to see a dead short here, and it's going to think it's a fire, and it's going to enunciate as fire zone number 3. And if the zone number 3 is programmed as the front lobby or whatever else, it's going to notify. And then the signal is going to be notified in the monitoring station that they're going to, and of course, people who are in the building are going to hear a bunch of noises and indication that they have to leave the building, things like that. All right. Now, also, what I have here is a Google Home for that for the monitoring, right? There are different ways of monitoring right now. Now, here's another example: security alarm. You see, here's the magnification of a board or a printed circuit board of security alarm. Here's the auxiliary terminal, so that's plus and minus, so it's like a 12-volt DC for the active devices. Active devices are the devices that need power to operate. Or door contacts will be not active, will be passive devices because they just open and close. So it's not based on if you have something that's called a reed switch mounted on the door frame, and on the door itself there's a magnet. If the magnet comes close to that switch, the switch closes, and basically it's a normal condition. If the door is open, the magnet goes away from the switch. So it's a passive device. It doesn't require electricity to operate. But if it's a motion sensor, yes, it has to have power to it because it has certain electronics that has to sense, or a glass break detector or something like that, right? This would be to provide the power for those devices. And then here, you can see here it says bus, right? And that bus, I drew I put a couple of keypads, and keypad is not smart device, it's an active device, and it's also a smart device because it communicates and it needs electricity to power itself, well, to be powered, right? So I just didn't draw the cables that supply the power, but they have to be there. But I just want to concentrate on the bus configuration. So here's the data line, and notice yellow and green, right? So here's the yellow wire. It goes and it's being connected to one of the keypads, and then goes and in parallel configuration also connected to another key, and keep going to whatever the amount of keypads the system is capable of handling as far as communication. Same with the green. All right. So basically those two keypads can independently communicate with the main circuit board by using a bus line. So even though the bus configuration is not used for the computer networks, but it still has various ways that's still being used. Zoom out. Next one here. Inline and chain topology. All right. Inline chain topology. So here's a ring topology for those two switches. Right. So these four switches are connected in a ring topology because the communication goes all the way around. Right? And inline or chain topology, these four switches are connected in a chain topology. So if this link gets broken, this switch is not communicating with that switch. Is bus an acronym? Here's a question. Find out. I'm going to find out as well. All right. So most of the switches would be connected in a ring topology. However, when you're going to look at some industrial devices like PLC or controls, you are going to see them being connected in a chain topology. And here is a topology symbol for the chain topology. Right? Now, what I'm going to do also is I'm going to give you the real life examples, because when you go into the real world there, if you get a job in this field, you should know the existence of some of the devices. We're going to start with something that's very simple. Here's a switch. Here's a switch. All right. Okay. Now here's a laptop or computer and a printer. Here's a computer and a printer. This workstation or computer is connected to a switch in a star topology, because every device home runs when it comes to connection, home runs to the main node. The advantage of that is that this printer can be used by multiple users in the office. If somebody really wants to have a personal printer or in a home configuration, you can connect the printer inline with the computer. So here is the star topology, here's the inline topology. Now, here's another device. This Ethernet extender is connected inline with the Ethernet link. Ethernet is a protocol that's being used to connect the LAN, to make the LAN connections, and that's how the devices are communicating with the switch using something that's called the Ethernet protocol, not internet, but Ethernet. Right? Now, the Ethernet link, when it comes to copper, is only able to carry the signal no longer than 328 feet. But for the simplicity, purpose of simplicity, or making things simple and easy to remember, 300 feet. So that's one. Also, the real other reason for that is that, well, end-to-end link, if you have 328 feet, that's it. But what about the connecting patch cords from the patch panel to the computer, and from the patch from the jack in the wall to the computer? It's going to have a few feet, so it's a little bit of reserve. So 300 feet end to end, no longer than that. But what if you have something that is kind of further than 300 feet when it comes to the wire length, because the wire has to go up, has to go maybe some routes in the ceiling, and it has to come down. So all that distance, it adds up pretty quick. So if it's further than 300 feet end to end, well, you won't be able to transfer data. You won't be able to communicate with the switch. But if the speed is not as important, then you can install something that is called an Ethernet extender. It's a smart device. It gets its power either from a jack in the wall somewhere. When it's close enough, you can have a transformer, and the power supply, and it could be powering up this Ethernet extender, or the power can be carried through the cable, because some switches are capable of providing something that's called power over Ethernet. It's PoE. Is this a PoE switch or is it not PoE switch? Some of the switches just provide the signal on the port. Some of the switches, the more expensive switches, are able to provide PoE signal as well. PoE is basically a DC, and usually it's 48 volts. So then the PoE can supply power to the Ethernet extender to actually power its electronics. and then the Ethernet extender can boost the signal and push it further than 300 feet ends to end. You get another 300 feet. Okay, if the speed is not important, then you can use that. Where the speed would not be important, well, if you have a video communication signal and you transfer a lot of video signal and computer graphics and so on, yes, you would need the speed for that. But let's say it's a POS, which would be a point of sale, basically a cash register in a store. It's in the form of a PC. Right? So speed is not that important because basically with every transaction, the cash register sends few numbers down to the main switch, and it's not important that it's in a lightning kind of a speed. So yeah, you can use something that's called the Ethernet extender for that. Well, so here's a device that you know that it exists. So here, well, we talked about PoE. This PoE injector is connected inline with the wireless access point. Wireless access points are smart devices and they're active devices, and they use Ethernet link to communicate with whatever the main node is, usually a switch. Well, if it needs to be mounted in the ceiling, quite often or most of the time, you're not going to have access to a power outlet. So you can plug in a power supply and power this power up this this wireless access point. Okay, so PoE is quite common when it comes to supplying power. But what if whatever the facility they had already installed a network running, and they purchased a few years before this decision was made to add those wireless access points, and those switches were not capable of providing PoE signal. They were the less expensive switches. Well, you can replace the whole switch, but that comes with reprogramming the whole thing and setting things up and everything else that is connected, the computers in the office and cash registers and whatever not. Or you can just get something that's called a PoE injector, right? So you put that between the wireless access point that needs power and the switch. The switch provides the signal to the PoE injector, and that would be in the rack location. So there'll be a lot of places to plug this thing in. And on the other side, it provides the signal along with the PoE power over Ethernet. That means that basically there's also a DC power present on that wire, and on the input side here, there's a circuitry to distinguish to catch the DC power supply signal and discriminate between that and the actual signal that is considered to be a data. So here's one more device that you know that exists. It is called a PoE injector. All right. Also, inline or chain topology, this VoIP telephone set is connected inline with the workstation computer. A lot of companies are switching from the regular or the conventional telephone systems to something that is called a VoIP telephone system, voice over Ethernet protocol. Right? So in order to make the changes convenient, because it's all about money, the companies who sell the VoIP telephone systems, they want things to be as easily installed as possible so more people can buy them, right? It translates into money. So what happens is that the companies who produce that, they produce the phones that can be connected inline with the existing network. So if the network jack was supplying the signal to the computer in somebody's office, in order to install a VoIP telephone system, you just unplug that and plug the telephone into the wall jack for the computer network, and the other port, it has two ports, input and output. It can provide the signal to the desktop computer. A very popular, again, in huge department stores. If somebody works in some of the huge department stores, you're going to see that happening a lot. You're going to have that sophisticated with the screen, LCD screen telephone. That's a VoIP telephone. And the connection is from that into the network and from that into the PC. And the signals are being distributed properly. So the computer still sees each signal, what it's supposed to do, and the phone also receives that its signal. So this VoIP telephone is installed in line with the workstation computer, right? Are the PCs connected to the switch in a ring configuration, or is it a star? Right? Right? So here's a switch. Yes, it looks like it's a star configuration, but can it be a logical topology? Can it be a ring? Yes, it can be. Right? So here is the switch with hardwired connection in the form of a star. But if for some reason somebody, it's a very hypothetical situation here, if somebody decided that the signal routing would be in a ring configuration, so it can be done. Why would somebody want to do it? I don't know, but I just want you to know the difference between the physical geometry and the signal routing, okay, the logical, right? So this would be connecting things in a star configuration, but the signal would run in a ring configuration. Is something like that being done? Not really, maybe, but I just want you to know the idea of it, all right? Just a couple more minutes. The next lab, after this, we are going to do the IDC. What does IDC stands for? Well, when you watch those prep videos, you're going to know exactly what IDC is, but it basically stands for Insulation Displacement Connection. We're going to do a punch down. So here's the Cat5e cable, and here's a Cat6 data cable. If you look close here, I'm not sure if you can see it or not, there is that plastic separator here in Cat6. Cat5e doesn't have that plastic separator. It just have a bunch of wires, has a bunch of wires in there. Notice that the pairs are twisted, and they're twisted at different rate. We'll talk about that later in details of what's happening. Basically, it's to eliminate the crosstalk, which means the interference between one pair or another, and they are twisted in different ways. So the interference between the pairs, or the crosstalk between pairs, is made not as easy. So the signals can stand on their own. And we'll talk about how it happens later. Right? So Cat5e is an earlier generation at Cat6. It does have twisted pair. Or it's a twisted pair. It's like 1, 2, 3, 4 twisted pairs. It's a twisted pair configuration. Cat6, it has pairs, but not only has the pairs that are twisted around themselves, but it also has a separator. It's just like a one of those, and it's also twisted as along. So the pairs are also twisted as they go along, right? So the interference is even harder to cause any problems there between the pairs. Here's the jack. Here's the patch panel. That's the front. That's the rear of the patch panel. So in some of the labs, we're going to terminate jacks, and there's also going to be a lab we're going to terminate a patch panel. All right. IDC, insulation displacement connection. Basically, what that is there's a wire that is insulated with insulation, and there's a knife like a connector spring-loaded towards itself. So when you force that conductor into this connector, those knife-like connection points, are going to bite into the insulation and make a connection with the wire. The only one thing is, I got this thing from the internet, it shows stranded wire. No. Oh no. All right. insulation displacement connection is made for solid wire, simply because if you bite into insulation, make a contact with the conductor that's inside, if it's stranded cable, some of the strands might be actually cut off, so it causes all kind of problems. So it's meant for a solid core conductor. There you go. And over here, that's how it's being done. If you watch those videos at your convenience before the lab, not this one, this is a PA system lab, one more week, and we're going to start the insulation displacement connections. We're going to terminate jacks and whatnot. And you can read a little bit of a history of that, so I'm not going to go through this, but that's basically the idea of it. All right. Okay, so that is the end of this class, this course, this lecture, this class. If somebody wants to stay and ask some questions, or maybe you want to have some other questions later on, you can ask me tomorrow before we start. Have a good afternoon, Professor. I guess I'm the professor. You have a good day too. Thank you so much, and I will see the rest of the class tomorrow. Take care, guys. All right, bye.